So I hinted at last time that just like other conservative forces, the gravitational force being conservative also has a potential energy function. And I didn't tell you exactly what it was. However, I made the argument, why do I have, I made the argument that because the gravitational force only depends on the distance r and the unit vector r hat, that the gravitational potential energy should only depend on that variable r. Much like how if you have a force that only depends on x and y, and only has the vectors I hat and j hat, your potential energy function only depends on x and y, right? R is a direction just like I, j, and k. And so because there are no other directions involved, in this case, these are spherical coordinates, we expect the potential energy to only depend on that coordinate, r. So we're going to go through that, and we're going to work this out rigorously, or semi-rigorously anyway. We're going to discuss the gravitational potential energy today. And it turns out the gravitational potential energy, knowing what it is, makes for a very useful tool, just like how potential energy in general is really useful. So in the past, we had we had that the potential energy due to gravity as a function of vertical position above the ground was, say, mgy plus maybe a constant. But that can't be used for the potential energy associated with the actual gravitational force, Newton's universal law of gravity, for a good reason. And that reason is U log, by the way, stands for universal law of gravitation. That reason is that the force from mgy is constant. And that's just because if you remember how the force is related to the potential energy, it's the negative derivative. So if you take the derivative of mgy with respect to y and stick a negative sign, you get a constant, you just get a number. And we know that the force from gravity, at least written as the universal law of gravity as it applies to everything, not just on the surface of the Earth, changes with distance. So we can't use that. That can't be the correct potential energy function for the force gmm over r squared. Now, what we can do is we can do what we did before when we were discussing potential energies to construct the potential energies just by doing an integral. And so we're going to do that. We're going to construct the potential energy like we typically would. So the force of gravity, in terms of variables x, y, and z, I'm actually going to give some setup here. So we're going to put the source of gravity at the origin. At positions x equals 0, y equals 0, and z equals 0. Then the force of gravity as a vector and a function of x, y, and z, because it depends on where the thing feeling the force is. This is equal to minus g, and I'm going to use capital M for the mass of the sourcing object and little m for the mass of the object that's feeling the gravity, divided by r squared times r hat. Now we can actually rewrite this a little bit. Notice that r, the vector, is equal to r times r hat. So this is the magnitude, this is the unit vector, and this is just the vector that points from the origin to the place of interest. I'm going to take this and put it aside. So we can actually use that to write out or to rewrite this expression. That would give us negative g mm over r cubed times r, the vector. So all I did was I just replaced r hat with r, the vector r divided by the magnitude r. That's all I did. But the reason we do that is because it's a little bit easier to write out what this vector is, because we're going to just write it out in terms of x, y, and z now. So continuing, remember, r is the vector xi hat plus, I don't need parentheses, it's xi hat plus yj hat plus zk hat. It is the vector that points from the origin to the point xyz. And so the magnitude is just square root of x squared plus y squared plus z squared. And so that's what this r cubed in the denominator is. So writing this out, we get minus gmm divided by x squared plus y squared plus z squared to the 3 halves, because you have to take a square root and there's 3 r's. And then we multiply that by the vector xi hat plus yj hat plus zk hat. And so that's what our force is in terms of x, y, and z. Now, I'm going to give you a calculus fact that you can verify. As an aside, my throat is very scratchy today. The partial derivative of the function x squared plus y squared plus z squared to the negative 1/2, this is equal to minus 1/2 times x squared plus y squared plus z squared to the minus 3/2. Yeah, that's a 3/2. Times 2x. And so written out, this is x divided by x squared plus y squared plus z squared to the 3/2. And so hopefully you can see why this is useful. So this term here is similar to each of the terms here. Right? You have x divided by the denominator and so on, y divided by the denominator, and so on and so forth. So this is a useful derivative. So, and yes, it should be. Sorry, I dropped a negative. And we also know what needs to be the case for a potential energy function to be the potential energy function for a force. Indeed, whatever the potential energy function for the gravitational force is, it needs to satisfy that the negative partial derivative with respect to x of that potential energy function, xyz, or u sub g of xyz, has to be equal to the force in the x direction. This has to be equal to gmm, and all I'm doing is I'm just rewriting that term as just a single object, times, and I'm doing a little bit of rearranging, x divided by x squared plus y squared plus z squared to the 3/2. Right? So you have a single x, you have a single g, you have big M, little m, you have a single minus sign, and then you have the denominator. So this is what needs to be true about u sub g of x, y, and z for the x coordinate. You can also do the same thing for the y and the z coordinates in order for u sub g to be the potential energy function. But we already know how to form this function, right? We know what you have to take the derivative of in order to get this thing, right? That was this whole point that I just made. If you take a derivative of x squared plus y squared plus z squared to the minus 1/2, you get what we wanted back out. And so what we find is that u sub g, x, y, and z, should be equal to minus g capital M little m divided by x squared plus y squared plus z squared to the 1/2 plus, and then we have to add, we're doing an integral, so we have to add a constant. We have to add something that's constant with respect to the other variables, or constant with respect to that variable. So this is our guess, right? Or this is our guess for what the potential energy function should be, and we still need to figure out what that function u naught of y and z is. But we know that if we take the derivative of this term, the negative partial derivative of this term, then we get the force in the x direction back. And so that's a good check. And in fact, we can check that if u naught is constant, then the negative partial derivative of y of this guy, x, y, and z, is equal to the force of gravity in the y direction. And similarly, the negative partial derivative in the z direction of u sub g, x, y, and z is the force of gravity in the z direction. And we can just read those off by looking at y divided by the denominator and z divided by the denominator respectively. So this just checks out. So indeed, the gravitational potential energy function is negative g big M little m over x squared plus y squared plus z squared to the 1/2 plus some constant. Now, we're not quite done because I did say something about how the potential energy function should only depend on the distance that the two objects are from each other, right? That was the whole point. It should only depend on r. But we have a trick up our sleeve. We can rewrite this using the fact that the letter r, or the variable r, which is the distance, is equal to the square root of x squared plus y squared plus z squared. That's just a true statement. That's how it's defined. And so what we're left with at the end of the day, after all of this business, we get that the potential energy is indeed just a function of the distance r, and it's equal to negative g big M little m divided by r plus a constant. And so that is the potential energy function for gravity, which is, it's actually like a really nice and simple formula, right? It started off with this big messy thing, but at the end of the day, we find that if you write this out, if you go through all this work, you find that this is what it has to be. And in fact, you could even double check. Just taking the negative partial derivative with respect to r of u sub g with respect, or of r, it is indeed g, and I need that guy. So the derivative will make that negative sign positive, but we have a negative sign in front, and then it points in the r hat direction. Sorry, no, that's, so this should be equal to this thing should be equal to the force in the r hat direction. And that's indeed what it is. This is the force in the r hat direction. So it checks out, which is a good thing. Just as an aside, we usually choose that the potential energy function at infinity, that the gravitational potential energy at an infinite distance away is 0. And so what that implies, this is just a convention, that the constant is 0. And the reason we do that is because we want things to have no potential energy when they're not interacting with each other. And if two things are infinitely far away from each other, they shouldn't be interacting. So that's just a choice that we didn't have to make, but it's a convenient one. And so simplifying one more time with that fact, we get that the potential energy is negative big M little m over r. And that is the standard potential energy function that you'll see in textbooks. Right, so it's a simple formula. It goes inversely with the distance, and so we can actually just plot it to figure out what it looks like. So g is positive, m is positive, but well, both m's are positive. And so if we were to plot this as a function of r, we find that it looks just something like this, right? Nothing too sneaky going on here, but there's a little bit of there is something sneaky that's been shoved in. So let me zoom in air quotes. We're going to zoom in on a small range of distances r. Say between, so we're going to look on the range where r is greater than r naught and less than r naught plus, say, h, where h is just some small number. And we're going to choose h is a lot smaller than r naught. So like it would be like looking for values of r from like, say, 10 kilometers to 10 kilometers and 2 meters, right? So we're just looking over that really narrow range values of r. Well, if you were to do that, if you were to zoom in and only look on those particular values, you'd find that the potential energy just looks like a line. This would be r naught plus h, and this would be r naught. It just looks like a line, and that shouldn't be surprising because that's how all functions work. So what have we been trying to do with gravity for the past couple minutes? So we figured out what the gravitational potential energy is, which is good. Now we're going to show how that's very closely related, or how the gravitational potential energy that we've worked with in the past, mgy, how that is just an approximation of this formula here. So this is approximately linear. This is u sub g, and this is r. And so the question is why is this linear? So we're going to do some calculus now. We're going to do a Taylor series expansion. About r equals r naught. So we want to expand u sub g of r naught plus h in terms of u sub g of r naught, and then the variable, and we're treating h as the variable. So we know that this should be equal to negative g capital M little m divided by r naught plus h. And now we just want to expand h, or expand this function in terms of the variable h for h being small. And so I'm not going to take you through the details, but you guys all know how to do Taylor series. So this is approximately equal to negative g big M little m divided by r naught plus big G big M little m divided by r naught squared times h minus gmm over r naught cubed h squared plus dot dot dot, right? That's how the expansion would end up looking. And we can factorize this, or factor this. So it's written out this way. 1 minus h over r naught plus, sorry, I need another minus sign. Wait a minute. 1 minus, yeah, this should be plus. There's a typo in the notes. Plus h over r naught squared minus dot dot dot, right? Oh no. Well, go catch up on your Taylor series. They're super useful for physics. It's just an approximation though. Taylor series are a way of approximating something for a small variable, like in a small range. And so it turns out that when h is significantly smaller than r naught, what we have is that h divided by r naught squared is significantly smaller than h divided by r naught. And so, so for small h, we can just drop everything that's h squared, or h over r naught quantity squared, and beyond. We get that u sub g of r naught plus h, this is just equal to, or let me put approximately equal to. I'm missing a minus sign in the, no, I'm not actually. It's approximately equal to gmm over r naught squared times h plus u naught, where u naught is equal to u sub g of r naught. This is just that first term is what it boils down to. The Taylor series is expanded about h equals 0. Yes. So maybe I should say, let me rephrase. I mean, they were expanding r about r naught and expanding h about h equals 0 are the same thing. But they do have different syntactic meanings. So let me just be more specific. So you take the constant term, you shove that into a u naught, which we'd never care about. And then the non-constant term, the first term of the Taylor series, is this guy. So why do we care about this? Well, now we can just choose whichever r naught we want. So, and this will still be a valid approximation. So we're going to let r naught be the radius of the Earth. And we're going to let the big mass be the mass of the Earth. Right? We're going to work in the specific case where we are approximating the gravitational potential energy of an object near the surface of the Earth, i.e. when slightly above the surface of the Earth, 8 units h above the surface of the Earth, which would be r naught plus h units from the center of the Earth, and the mass of the object is the Earth. So we're approximating this for the surface of the Earth. So we're letting r naught be the radius of the Earth, m be the mass of the Earth. We're going to let h be significantly smaller than the radius of the Earth, That has to be true, otherwise this approximation fails. And so all of these together, these approximate u sub g near the surface of the Earth. And so doing so, we find that the gravitational potential energy, as a function of h now, because the variable r naught is just a fixed number, it's just the radius of the Earth. This is m times gm over r naught, sorry, g little me times re divided by re squared times h plus u naught, which is just some constant, so we don't care about it. But remember that this is g, so this is just mgh plus u naught. And so this is where that mgh comes from for the potential energy. It's just for the potential energy near the surface of the Earth. It's just an approximation from the general potential energy for gravity. If you take this potential energy and then you expand it about the distance being the radius of the Earth, or equivalently about the height above the surface of the Earth being small, and then you plug in the standard variables for the standard parameters for the Earth, you end up getting precisely that u sub g, potential energy as a function of height above the surface of the Earth, is just mgh plus some constant. Now, again, we're throwing away some detail here. We're throwing away that the second order term. So you could have kept the second order term, and you would have something that goes as h squared divided by the radius of the Earth squared, or sorry, divided by the radius of the Earth, which would be very, very small, and so that's why it's safe to neglect it. We're just keeping the first non-trivial term, and it's a thing that we do in physics a lot. But this is where that comes from. Now, the reason why we talked about potential energy, the gravitational potential energy at all, is one, this is going to show up on homework, so it's good for you to know what it is. But two, knowing the potential energy function for a force is really useful because it lets you simplify otherwise very hard problems. Like you can use, for example, energy diagrams to try to graphically understand something that might otherwise be hard to grasp. So we're going to do that here. We're going to use our new potential energy with energy diagrams to learn about orbits. Oops. So recall that once we had the potential energy function for some force, as long as that's the only force acting on an object, we could use energy diagrams to figure out, say, what the minimum distance is that one object is from the origin. Things like that. We could figure out whether the object is in a stable equilibrium or an unstable equilibrium. We could figure out how far away it could get before it turns away. We could figure out all sorts of things. We could figure out if it was bound, if it was not bound, and so on. But in order to use energy diagrams, we need one-dimensional motion. Right, all of our energy diagrams that we've done in the past have been like the potential energy for a spring, like 1/2 kx squared, and then we ignore any motion that's not in the along the x-axis. So we have one-dimensional motion. The object moves along the x-axis and the force is along the x-axis. However, in this case, where we have gravitational potential energy, it's not one-dimensional motion. It's in principle, it's three-dimensional motion. In general, or more specifically though, because at least for stable orbits, the motion takes place in an ellipse, which means it's two-dimensional motion. So how is it that we can use an energy diagram to describe this type of motion? So, and the trick is, the answer is yes, we can cast gravitational dynamics in terms of 1D motion, effective 1D motion. But it takes a little bit of finesse. So let me explain why it needs a little bit of finesse. So let's just imagine that we could just treat r as our one-dimensional variable, and that's it. we would just imagine that it's a one-dimensional variable and the object just moves along R, and we can just plot it. So we would have our gravitational potential energy. We plot it like this. It's a terrible drawing. So we have U sub G, we have R, and let's say that, let's say that the object is here, and it's moving towards the perihelion. Say that this position here is the perihelion. And it's moving towards the perihelion with some speed v. So we can figure out what the total energy is by figuring out its potential energy, adding to it its kinetic energy, and so on. But it's moving towards it with some speed. Now, we know that if an object is in orbit, or in particular, if the object, as long as the object is not traveling straight at the source of the gravity, we know that the object will swing back around and be shot back out to continue its orbit, right? But in this model, where we just assume everything works out handy-dandy and R is just a 1D coordinate, we would predict, remember, objects move towards lower potential energy, so it would fall down, it would infinitely. We'd predict that the object just falls into the sun. And not that it turns around and goes back out and goes back to the aphelion. So how can we capture that sort of phenomenon, that the object doesn't just continue falling towards the sun and in fact gets close to the sun and then moves back out with an energy diagram? It seems like that would be difficult. And so just treating it naively as a one-dimensional motion doesn't capture this turnaround behavior. And the reason for that is because we didn't give the, it's not quite like a spring. The reason for that is that we didn't give any sort of information about the other dimensions of motion, right? So if indeed you just pointed an object straight at the sun and fired it with some speed, yes, that object would hit the sun. It would just fall towards the sun and it would just hit the sun. But that's not what we're trying to model. We're trying to model a system where it has some speed it's maybe not pointed at the sun, it's pointed at somewhere else, and it'll go around the sun. And so that involves some motion that's not directly towards or away from the sun. So how do we involve that motion? How do we involve that motion in an otherwise one-dimensional plot? And it turns out that there is a way to do this. It just requires a rewriting. So we need to be able to, the purpose or the reason why this went wrong is because the kinetic energy in this plot, or the kinetic energy that we would typically use, has multiple terms, right? It's 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. It's not just 1/2 mvr squared. So we need to break it up. We need to break up that kinetic energy into multiple pieces. The total kinetic energy in terms of energy that's due to motion towards the object in the r direction and motion that's not in the r direction. In terms of energy due to the motion in the r direction. And then we need to recast the other energy, like the other components of the kinetic energy, into a potential energy. So the point is because we can only discuss kinetic energy, because like a two-dimensional energy diagram can only handle motion that's along the axis, that is the horizontal axis, so in the r direction in this case. Anything else that depends on motion that's in any other direction has to be shoved off and accounted for in a different way. But keep in mind that it doesn't matter what you call these things. You can call it kinetic energy or call it potential energy, as long as you're not changing the total energy. If you can somehow rewrite the kinetic energy associated with the motion that's not pointing towards the source of the gravitational field as a potential energy, i.e. in terms of the variable r, not the direction r, but the variable r, then you're golden. So just as an example, we didn't include 1/2 mvy squared in the kinetic energy when handling, say, the gravitational or the potential energy that's just a function of x in energy diagrams. We just didn't do that. So we can't do that here. We can't consider motion that's not in the direction of r and include it in this energy diagram as a kinetic energy. So what's the fix? We write that the kinetic energy, the total kinetic energy of an orbiting body, is the kinetic energy in the radial direction. This is the kinetic energy that associated with motion in the r direction, plus kinetic energy that is tangential to a circle that describes the direction of motion. So let me draw a picture. So let's say that we have, let me draw a better picture. Let's say that we have our orbit, something like this. It's a terrible ellipse. There we go, orbit like this. There's our focus that we're orbiting around. That's our r equals 0. That's our origin, basically. So if our object is on our orbit, has some velocity, say this way, which it does because that's the direction it's moving in, well, we could break it up into a velocity component that's this way and a velocity component that's perpendicular to that. But conveniently, imagine instead that at that moment, the circle, or you could imagine that it's moving, sorry, how do I want to phrase this? We don't even need to draw the circle. We can just break it up into two components. One of the components is the direction towards the object, and the other one is at a right angle. You could break up the velocity into two parts. So we have the radial direction here and the tangential direction here. And the reason we call it tangential is just because if you drew a circle that point was passing through, that the tangential would point tangent to the circle. That's all. So this is V here. So the point is that the tangential kinetic energy, tangential component of the kinetic energy, is just 1/2 mv tangential squared. And now we can use a trick. So recall that the angular momentum of an object, it's mv r perp, right? That's one way that you could write it. So in this case, it's mvr sine theta. This is the magnitude of the angular momentum, where sine theta is the angle between the vector v and the vector r. So this angle here is theta. And so we can group this as mr times v sine theta. Right, I know that this seems out of left field, but bear with me. This quantity here, that is the tangential velocity. V sine theta, like you can work out the trig yourself, that is the tangential component of the velocity. And so what that implies is that the angular momentum is in fact just mr times v tangential. And that shouldn't be surprising, right? The angular momentum is m times the distance times the velocity that's perpendicular to the vector r that points from the origin. In this case, from here to the point of the object, right? That's one way to write. We've written mr v perp before. In this case, v perp is what we're calling v tangential because it's perpendicular to the radial component. And so we can rearrange this and we get that v tangential is equal to L over mr. And now we can see that we could rewrite the kinetic energy of the tangent, or the tangential part of the kinetic energy in terms of just the distance r and something that's constant L, i.e. the tangential kinetic energy is just L over 2m r squared. Substitute in V tan is L over mr, do some simplification, and this is what you're left with. And that's really good. That's really super useful, because then the total energy of the orbiting system is, well, let's write it out. E total is the kinetic energy in the radial direction plus the kinetic energy in the tangential direction plus the gravitational potential energy, right? That's just always there. And so substituting in, we get 1/2 mvr squared plus L over 2m r squared minus, and I'm dropping the constant here because it doesn't matter, minus gmm over r. And the important point is that now the kinetic energy only, like, even though the kinetic energy really, even though the motion really is two-dimensional, the kinetic, there's only one term that depends on the velocity. On the velocity, and that's a term that depends only on the radial component of the velocity. So the kinetic energy in our system, the kinetic energy, we just call 1/2 mvr squared. And that's totally allowed. That would be a totally valid kinetic energy for an energy diagram. And then the rest of it only depends on the distance r. So that would be a perfectly valid potential energy. So we can treat this as a 1D system then. But even though it fully encapsulates the 2D motion. Whereas before, when we had 1/2 mvr squared plus 1/2 mv t squared, then there were two separate kinetic energies that were that relied on different directions of motion. The bottom line is that all of the motion that is not in the radial direction is captured by L over 2mr squared. So we have a new potential energy function. And we call it the effective potential. It's what the potential would be effectively if we treated all the tangential motion, or if we combined the energy associated with tangential motion into a potential energy. And so that can then be written as U sub f of r. Notice it still only depends on the distance, r. L squared, oh, wait a minute. I think I dropped an L somewhere. Yeah, that should be L squared. That should be L squared there. My bad. L squared over 2mr squared minus gmm over r. And so this potential energy, it's not actually a potential energy. The first term is specific to ellipses because I'm circular orbit. Yes, that's precisely it. For a circular orbit, the kinetic energy is, there is no kinetic energy in the sense that there is no radial component. Yeah, and we will get to that. So we can plot this now. And now it should all start to make sense. So I'm going to plot energy. Let me do a big plot so that you can see what's happening. I'll put our radial vector, or our radial coordinate, radial axis here. And so now, if we were to plot this, it would look something like this. So it should actually look very familiar. It's not the same as the Leonard-Jones potential, but it's very, very similar. So this line would be, sorry, not that line. Oh no. Okay, I guess I'm redrawing it. So maybe so let's just, this is the effective potential. Let's just give our system some energy. Let's say that it has this much energy. That's E tote, right? That's what we typically do. So then this point, that distance there is the perihelion distance. This point here, that would be the aphelion distance. And then maybe this point here, maybe we call that R naught. That's the well, actually, it doesn't really have a whole lot of meaning, so I'm not even going to label it. It's the minimum value. It's the yeah. I'm not even going to bother labeling it. But so now you can see that if an object is falling towards the sun, it'll with this much energy, it'll go down, gain a whole bunch of speed. Well, gain a whole bunch of radial speed. This is the point where it has radial speed. It'll swing back up, but it can only get up to this distance. Because at that point, the potential energy, the effective potential energy, is equal to the total energy that the system has. And that's not saying that it only has gravitational potential energy. Keep in mind, the effective potential energy also accounts for tangential velocity, energy associated with tangential motion. So this at this point, all of the motion is tangential. And that has to be the case because there's no radial motion anymore. So here, the turnaround points actually make sense. So they make sense because it lets us see what happens if you get too close to the sun. If you have some angular momentum L, as you get closer and closer to the sun, your L is constant because there's no change in angular momentum. Sorry, there's no external torques. And so as your distance from the sun decreases, in order to keep L the same, the angular momentum, you have to increase your radial velocity, which increases your which increases the value of the effective potential. So it kind of makes sense that as your distance to the source of gravity decreases, the effective potential shoots up really, really fast. And that's just because they're inversely related to each other. Like you can see that this tangential term is, L is inversely related to the distance. It has to be for a fixed energy. And so maybe I'll just leave it at that. So this is a way to understand orbital dynamics. So the reason why you get this effect where it seems to pop up even though there's no actual energy there is this is often called a like an angular momentum barrier, meaning you have so much your system has so much angular momentum that if you were to just crash into the object, crashing into the object would amount to having no angular momentum left. So instead, this large angular momentum that you have, because it has to be maintained, forces you to swing around. Because if you didn't swing around, then your angular momentum would be changing. And so that's why there's this barrier, this part over here, that prevents you from crashing into the sun. So this is all to say, if you're orbiting the sun, say in a spacecraft or something, it's actually very hard to hit the sun because there's a large energy barrier, that part, that will force you to go around the sun unless you unless you either take away sufficient energy or add sufficient energy in the correct way. And we can talk about that after lecture if you guys want. I'm just going to say one or two more things and then we'll be done. So just as a word of caution here, when the total energy is equal to the effective potential energy, that, i.e. when they're matching, i.e. at these points, that doesn't mean that the kinetic energy is zero. It just means that the radial component is zero. Which just means that all of its motion is tangential to its, or is perpendicular to the radial vector. Is there a tangential velocity big enough to break orbit? Yeah, sure. Yeah. So I'm going to stop here. we have some more to do regarding this this whole business of energy diagrams for gravitational dynamics, but we'll continue that on Wednesday. Sorry, on Friday. Today's Wednesday.